Hi, everyone there at GNU Radio Conference. My name's Haydn Nelson. I'm the Ettus Research Marketing Manager, and today I'm joined here by Abhay Samant. He's our Chief Software Engineer for our Aerospace and Defense Business Unit and our Systems R&D team. It's quite a long title you got there, but we pre-recorded this for the conference here at GNU Radio. I will be there in person. Abhay, sadly, will not be there in person. We're excited to be here again and again be the Diamond sponsor. And so today, we want to share with you some new capabilities for communications, radar, and EW, and an SDR-based research platform we've been working on. So with that, let's get started. So the title of our talk, new capabilities for comms, radar, and EW with an SDR-based research platform. It's a lot of words. And so really we're going to break it down into two sections here today. I'm going to talk a little bit about some of the investments we've been making in communications, research technology. Namely, the Universal Software Radio Peripheral, or the USRP, is a key to that. And at NI and Ettus Research, we talk to a lot of people in the wireless world, and we've kind of spoke to leaders in aerospace and defense, commercial wireless, people doing automotive radars in the transportation industries. We hear the stories of people employing wireless technology for a number of different applications, communication being one of them, sensing for autonomous driving, military radar, commercial radar, and the evolution of the wireless world is really transforming a lot of things for us in terms of the way that we use this technology. And across all those different applications, we've seen a lot of commonalities. People are increasingly wanting these things to be really adaptive, these technologies to be adaptive, to be able to rapidly transition them to new capabilities and to be customized for their specific application. And that lends itself to software-defined radio or software-defined technologies is going to be a critical piece of this. So us in the software-defined radio world have a huge advantage here that we've all been very enthusiastic about this technology for many, many years, and it's becoming increasingly more important as a base technology to enable all these future applications. Within all those applications, there's a lot of diversity in terms of waveform types. Some commonalities exist from radar, EW, communications, and we see people needing higher frequency, wider bandwidths, and multi-channel. I remember sitting at GNU Radio Conference 2018 when we were we actually had our sponsor presentation there in Las Vegas, and we were quizzing the audience. It was kind of funny. We had people. We said, "Hey, who here needs higher frequency?" And then a bunch of hands would come up, and then we'd have who needs wider bandwidth, and a whole bunch of hands would come up. And we were sitting there in that big conference room in Vegas, and we've taken some of that feedback from the open source and software-defined radio community that we've learned over the years and employed it into our product technology to be able to meet these requirements to go forward. And when we look at 5G, there's a lot of applications that are going to take advantage of 5G, and 5G has a lot of new technology built into it with massive MIMO, low latency modes, and that's going to enable a lot of really cool applications. I can't wait for the day where I get my Amazon drone to deliver my USRP B200 Mini to my front door. But that really comes down to wireless cognition, wireless sensing, immersive XR. There will be a lot of these applications that we'll see in the future based on this wireless technology. And now as 5G comes to bear, we're looking at what vectors are we going to need to innovate for 6G technology and communications? And that's really going to come down to, of course, more throughput. That's everyone, needs more throughput, but things like ultra reliability, when we're talking about autonomous vehicles and these things that are safety critical, reliability becomes key because, nobody wants their autonomous car to crash. And that's really going to mean a lot of innovation on certain technologies like extreme MIMO, joint communication and sensing, and we've seen that in both the commercial space and the aerospace and defense arenas. And when we look at the requirements for some of the enabling technologies that could drive 6G is really evolving the capabilities of MIMO, sub-terahertz, joint communication and sensing, machine learning and artificial intelligence. All these technologies are going to be driving factors to make what 6G will become. And so we've looked at all these different things and said, all right, what do we need to bring to the engineer out there to be able to prove this technology today? And so that is, some of you may have already seen this latest USRP in our product line was really specifically designed to meet some of these challenges and requirements in the market. And here it is stacked up against the rest of the Ettus Research USRP portfolio, which many of you in the audience know and love and are heavy users of. And the USRP X410 is the latest incarnation of the USRP, or Universal Software Radio Peripheral. So you can see here on the right that it meets or exceeds the performance standards on almost all the metrics here: frequency, bandwidth, number of channels. So suffice it to say, we went very high end on this product, and it is an evolution of the X series, the high performance series of USRP. It's a new platform that we intend to innovate on going into the future. And so, I already talked about the RF capabilities. Inside the digital capabilities of this radio, we're also designed to meet those future requirements of defense and communications applications. It's built on the state-of-the-art Xilinx UltraScale Plus RFSoC. Now, this is a really cool chip that has a lot of technology built inside of it, and it's you can kind of see here some of those specifications. What's inside this chip is really cool because it's more than just an FPGA. It has A to D's, DACs, highly integrated device with embedded processors. It has 4 application processing units, 2 real-time processing units, large streaming DSP fabric. It has 8 multi-gigabit transceivers for high-speed digital interfacing. So it's not only the RF and analog, but once you get that data, how do you get it off to be able to apply your machine learning algorithms on that data in a real-time fashion, maybe in a GPU. So it has not only high-speed analog interfaces, but very high-speed digital interfaces, as well as a whole lot of inline signal processing and a number of other features built into the radio. So suffice to say, it's a pretty high-tech radio. And of course, it's software-defined radio. It wouldn't be SDR if it didn't support a whole lot of software. Of course, GNU Radio is critical. Open source is very important to us. And you'll notice that the name of it is a little weird for those in the community. The NI Ettus USRP X410, because traditionally we've had National Instruments radios or NI radios, as well as Ettus Research radios, and now people mostly said, "Oh, Ettus Research radios, those are only for open source users." Well, no, and then we'd have NI radios, and those worked on LabVIEW and other tools. Well, this radio is intended to be the best of both worlds of the Ettus Research radios as well as the NI USRPs, that it can support all the tool chains in a single radio. It incorporates embedded processors like our N series, as well as high performance FPGA like our X series. So it's really the culmination of all the innovation over the many years of Ettus Research culminate into this really high performance radio. So that's why we said we didn't want to communicate to people this is an NI radio or an Ettus Research radio. It's an NI Ettus radio because it does pretty much everything, the best of many of these radios that folks in the community know and love. So I just wanted to highlight that. And I'm an FPGA guy, and it has the most FPGA resources of any NI product, even some of our PXI FlexRio FPGA-based UltraScale Plus. So we looked at those requirements and said, hey, there's going to be a lot of need for high performance streaming, and we don't want the FPGA to be a limiting factor. And so this RFSoC has a lot more FPGA resources on it, suffice to say. So here's the front of the radio. It's pretty cool. Come by and take a look. You'll note one striking omission here that if I was in the audience here, I would poll the audience and see if you could identify it. You'll notice there's no local oscillator imports and exports on this radio, which is important for people wanting to do phase-aligned multi-channel synchronization. And this radio is we decided to not include that feature on this particular radio, ultimately to keep the cost at a reasonable level that for the applications of which we think people are going to use this. So I just wanted to highlight that. You can do some level of phase alignment here with some digital controls of the VCOs and local oscillators internally, but there is no local oscillator import and export. But it does have 4 channels in and 4 channels out. And you can take a look on the back. It does have timing alignment capability with a 1 PPS and a 10 megahertz clock. So you can do time aligned operation with this radio using a GPS DO on board. And it also has, as you can see here, we have the PCI Express Gen 3x8 and 2 QSFP28s for dual 10 gigabit Ethernet off the back. And then just some command and control interfaces, as you would expect. So that's the USRP X410. It's already out there. We released it a couple months ago, mid 2021. Pretty excited about it. There's people already putting it to use using open air interface for 5G test beds. I'm aware of several research institutes that have gotten that working. One of our early customers of it was a company called 3DB Labs. They've done a lot of great work, and they have some advanced signals intelligence software. And you'll see here a little picture. They actually came to Austin and did a demonstration in studio, and I was really impressed with their Scepter software for signals intelligence. It's kind of the Swiss Army knife of spectral awareness, and and with the X410, it's even more capable because they have a lot more channels and a lot more, a lot wider bandwidth. And of course, it's GNU Radio ready. GNU Radio is an amazing open source community-based software tool that we are heavy supporters of, as well as RFNoC, which many of you know and love. So go to ni.com/SDR or Ettus.com. We'll be here at GNU Radio Conference. Come by our booth. We'll have one of these in the booth, or you can go to our virtual booth to see some of the demonstrations. With that, I'm going to transition to the next segment of our presentation, and we're going to talk about radar and EW research platforms for SDR. So NI has a strong history of multi-channel systems. You can see a couple examples of them here on the right. The top is a massive MIMO system we put together to prove massive MIMO would be a viable technology for 5G. They broke a spectral record with this system, synchronized multi-channel system. The bottom, this was a system done with DARPA for a mass channel emulator for proving that machine learning and AI is a viable technology for spectral cognition. And so we have a pretty strong history of building these systems, and we're continuing with that. And Abhay Samant here is going to share with you some investments in system level offerings we've been putting together for multi-channel system radar EW research platforms for SDR. Thank you, Abhay, for coming.
The radar and EW research platform reference architecture contains various components that NI has put together in order to enable researchers such as yourself working in the radar and electronic warfare space who want to simulate different types of algorithms, create different types of algorithms. But once they have those algorithms are proven out on a simulation platform, we also want to try running those algorithms on real world hardware with real world signals. One of the challenges that we have learned talking to many customers is while the development of the algorithms is difficult by itself, getting the infrastructure right to implement those algorithms on a hardware platform makes the problem even a little bit more challenging. So while you as customers are definitely the domain experts in radar and EW, National Instruments, we are trying to make it easier for you with the infrastructure piece. And that's kind of the underlying reason why we decided to embark on this journey to build this reference architecture. This reference architecture has the following key features. First of all, we have detailed documentation that describes how you can put such a test bed together, especially when you're trying to do multi-channel synchronization and streaming of data from all these channels onto a powerful server. We have implemented different software elements in a modular fashion so that you can put together these kind of systems. And in addition to providing the documentation on how to implement such a system, we have instantiated one system itself, which is the 32-channel, multi-channel, 32 channels phase synchronous system that is shown in this slide over here. This system, the 32-channel system, has a powerful server. We recommend two instances of server. One is a AMD-based server, and other is a server based on a latest chip from Intel. We also provide you the network and the system topology on how you share the multiple local oscillator signals together in a way to the extent of also providing the cable lengths so that you have no phase delta between the multiple channels. And also we talk about how do you do the system calibration so that you can minimize any of the drift that you see when your experiments are running for a longer period of time. In addition to the hardware elements, we have also focused on the software components of it. So yes, we have the benchmark rate example in the UHD driver, which is a good starting point, but we have taken it to the next step higher, where we have optimized the benchmark rate example by adding things such as streaming engines, by looking for the optimal way to write those programs so that you can get high data rate streaming from these large number of channels into a powerful server. The open source software is built in C++, and it will be available on the Ettus GitHub page. For the 32 channel system that we have put together in the lab, we also provide the system specifications for how the phase difference between the multiple channel is repeatable from run to run with a session reset, and also as we change configurations such as power level and frequency level. In addition to that, the reference architecture also provides streaming specification numbers as to the amount of data that can be streamed from these multiple channels. Now, one of the things that we have focused on a lot is what we have seen is you get certain data rates as you are looking at 1 or 2 channels, but as you scale from 1 channel to 32 channels, often we see that the data rates drop down. The reference architecture has special features in it to ensure that the data rate stays consistent as the number of channels scale. All of the reference architecture will be supported using the standard NI technical consulting services. And we also have documentation in how, once this data is streamed to the server, how you can integrate it with MATLAB or with GPU libraries. So why are we doing all these things? Well, we're doing all these things so that once you have your, say, machine learning and AI algorithm implemented, you can then quickly take all this data from real world environments and then see how your machine learning algorithms perform in those scenarios. So let me demonstrate that with an example. Say you're writing one of the new reinforcement learning algorithms, and for those of you who are new to this topic, in reinforcement learning, the idea is that rather than relying on pre-acquired, supervised or unsupervised, or labeled or unlabeled data, you are essentially sensing the environment in real time, acquiring that signal, and then making decisions on how your algorithms need to evolve so that you can make better decisions, whether it could be for spectral cognition or better usage of the spectrum. Well, in that case, a reference architecture like what we have put together will require you to have multiple of these sensors all synchronized together so that there is no timing or phase difference introduced from the test bed itself, and then you can focus purely on the algorithm that you are developing. So that is one of the applications that can be enabled by this reference architecture that we have put together. The whole idea, once again, is that you're focused on improvising and improving your algorithms while leaving the hard work of setting up the testbed infrastructure over to us at National Instruments. So let's zoom in a little bit more on the reference architecture. We looked at a portfolio of USRPs that are available from the NI and Ettus Research brand. And the one that from that portfolio we choose to focus on is the N320, N321. Here are some of the key specs of that radio. One of the main reasons why we chose this Ettus radio is because of the LO sharing capabilities that it has. So on a single unit, you have the capability to synchronize the local oscillators or use a common local oscillator for all the radios that are on these devices. And that is why in this reference architecture for the multi-channel application, we recommend you using the N320, N321, and that's what we have used as well. Here is a picture of how you do the local oscillator distribution within the N321. It essentially can take, there are two flavors of the N32X series. It is the N320 and the N321. And you can use one of them as a main radio that you have. And then other ones can be the child radios of that, which are inheriting the distribution. We have a splitter recommended in the reference architecture that shows you how to take the signal from one device and then split it and share it among the multiple devices. The splitter that we have recommended is what we have used in our system configuration as well, in the system that we have instantiated as well. So that when we look at the numbers that we get for a phase drift over a period of time or from run to run, any of the differences that are coming from the splitter are calibrated out as well. So when you're using the reference architecture, while you have the freedom of replacing different components, our recommendation would be to use the system components that we are recommending so that you can quickly reproduce the type of system specifications that we are seeing. The type of numbers that we are seeing, for example, we can get over a 24-hour run. We are seeing phase difference drift of less than a degree across the multiple channels. Let's look at the software architecture of the reference architecture. It's built on the UHT driver. The operating system that is built on is Ubuntu 20.04. We have tested both with UHT 4.0 release and also the 4.1 release. On top of that, we are using third-party network interface drivers. We have tested the reference architecture with the Intel X410 and the E810 network interface cards, and also with the Mellanox networks interface cards. And then the reference examples that we are providing built on top of that. When you see the reference examples that we ship, you'll notice that we have built it in a modular fashion so that you can run the example as it is in a monolithic form, or you can take pieces of these examples and then build your own application as well. The second thing we also done in all the reference examples is that we have provided a configuration script so that automation of some of these examples becomes easier rather than you having to manually type in all of these long commands. And trust me, it is one thing to type in manually for one radio, but when you're trying to control 16 different radios, you don't want to be manually typing in this. So the configuration files makes that process much more error-free and also more prone or more productive for automation. In addition to the software, the reference architecture also contains interconnect diagrams, a wire list that you can hand over to your technician who can put these systems together, and also contains assembly instructions for how to assemble the system. In terms of hardware, I've already spoken about the LO sharing. We also share the clock and the reference signals, and that is also demonstrated as part of the reference architecture as to what is the optimal location for these octo clocks and what are the cables that you should be connecting between these different octo clocks. The system instantiation that we have done is set up in a loopback fashion, where we use the generator on the USRP for generating the signal and then loop it back and do the analysis on that. Finally, I would like to talk to you about the actual topology that we have both for the data movement and for the synchronization. On the left-hand side, you see how we have set up the data movement between the CPUs and the different other processing cards that we have in the server, which are a combination of GPU cards from NVIDIA and also some FPGA cards. And so the data is shared over this network, and then we have further optimized the code so that we can get high streaming data rates from all of the channels over to a central location in the server. Once the data comes to the server, we have created some examples using the MathWorks tools so that we can see how the MathWorks libraries can then work on this data that is stored onto the memory and then do further radar processing on it. We also demonstrate in the reference architecture how the data can be stored on a disk so that it can be used for post-processing as well. On the synchronization, the way we have described the reference architecture, we can start with a 32-channel system, but if your application requires an 8-channel system or a 16-channel system, you can remove some pieces of the reference architecture and then have it scaled down to 8 or 16 channels, or scaled up to 64 or 128 channels as well. So the overall goal between the software, hardware, the network topology, and the system interconnect diagram is that you can quickly set up the system and reproduce the specification for synchronization and streaming that we're seeing in the labs, and focus more on the algorithms that you're trying to build. Thank you for your attention.
All right. Well, thank you for that overview of the system, Abhay. And actually, we have one of our systems R&D engineers over in the lab, and he's going to give us a quick tour of the actual system that we're working with over in the lab. Let's take it over to Jovian Wysocki.
Hi, I'm Jovian Wysocki, Systems R&D Engineer for NI's Aerospace and Defense Business Unit. Today, I'd like to briefly walk through an instance of our RF multi-channel research testbed. This instance of our reference architecture is built on the USRP hardware driver using USRP N321s and N320s. This system here is a 32-channel system composed of 16 USRPs. It's a combination of N320s and N321s all hooked up to 10 gig connections. It's more than just putting radios in a rack. We've specified the topology for LO and clock distribution. You can see here, we have a lot of wires. It can get kind of messy. These wires are for the LO. It goes to all 32 channels coherently. We've done the hard work, and we want to share what we've learned building this system with y'all. Now, multi-channel synchronization is more than LO distribution. We are also distributing the 10 megahertz and PPS to each radio through the octoclocks in the back. Our system documentation specifies all of the hardware requirements for you to duplicate this same system, along with some critical assembly suggestions for cable management and location of the USRPs. The hardware is just the first piece. We've also built considerable software infrastructure to simplify the process of getting started. Now, everything is running off of the Ubuntu 20.04 installation. All the code will be openly available on the Ettus GitHub. We've included several examples to show you how to achieve the same multi-channel performance that we have. We've designed the code to be modular and ready to incorporate your algorithms without having to build all the infrastructure of such a complex system. The code is built around configuration files, and these configuration files input the parameters for each parameter. The power level, the number of samples, the sampling rate, etc. As we currently finalize the first revision of this reference architecture, we have plans to deliver more capable and future enhancements to this. Now, let's hand it back to Abhay to share some of these system performance numbers we were able to achieve. Thank you for your attention.
All right, thank you, Jovian, over their little editing magic there to go to and from the lab super quickly. But we appreciate the quick tour through the system. It's pretty neat to see that whole thing put together. So Jovian had mentioned that y'all have done a significant amount of characterization of that system on the multiple channels. What can you say of where y'all are at in that process, and what are those numbers looking like?
That's a good question. It's still work in progress, but the numbers that we're seeing today are very encouraging. Mm-hmm. Let me give you an example. Across 32 channels, when I measured the phase drift over, say, 24-hour period, we're seeing phase difference of less than 1 degree over that time frame. Also, when I look at the phase offset between the 32 channels, that also is less than a couple of degrees. And the neat part is, as we go from run to run or from device reset to device reset, we're able to keep that consistently. So there's good repeatability, and that's also we're seeing, which is extremely important for our customers, because they want to make sure that the algorithms are going to stay stable, and whatever they're seeing from the test system can be calibrated out. So we are excited both about the streaming and the synchronization numbers that we're seeing, and hopefully by the end of this month, we should have all the numbers ready to be published on Ettus website. Okay,
yeah, that's, I will say that we're pre-recording this. Well, one, I can recognize the challenge and the need for that phase stability. I've seen a number of customers go through this. Nobody wants to recalibrate phase calibration all the time from run to run. That's not fun for anyone. We're pre-recording this for GNU Radio Conference. I will be there in person as well as Jovan Wysocki, and we should have some more performance numbers. If you want to come by the booth and talk to us, we're happy to share some of those. And like you said, as we finalize the development of the system, we will be publishing not only the code and all the reference architecture documentation on GitHub. We're also going to be putting some of those system level performance numbers on kb.ettus.com. So I don't know. That's pretty cool. I mean, I guess tying it all back together is that we've talked about communications, radar, and EW. We've shown you the new technologies we've developed with the NI Ettus USRP X410 that's really targeted at those next generation communication systems, and we're pretty excited about that radio and what the software-defined radio communication or community, are going to do with that cool new technology, as well as how people are going to take these system-level offerings that we're putting together to kind of innovate what's next. And so, with that, we appreciate your time, and please come by our booth or come by our virtual booth at the show. Like I said, I will be there in person. Excited to actually go somewhere other than I'm actually in the office today, other than my kitchen during this pandemic, and get out there and re-engage with the community. And we're excited to again be a Diamond sponsor here at GNU Radio Conference and continue our support for this amazing community. Anyway, thank you for your attention, and see you later at the event.